Hello, and welcome to day 2 of solving trig equations. Okay, a lot of what we're going to be doing, we're going to start off, it's going to look very similar to what we did in the previous lesson. I will say that one difference is going to be how many answers we need to write down. Okay, if you look at the directions, it says solve each equation for... And what this is saying is we want all x's or thetas or alphas, whatever variable that we're using, we want all solutions between 0 and 2 pi. So we want every single angle within one revolution, but we're not going to write all those repeats that we did the other day. Okay, once we understand that these there's an infinite number of solutions and these go on forever and ever and ever, we're good. And we're just now going to find all the ones within one circle. Okay, so if you look at the first example, this is very similar to something we would have done yesterday. So we're going to solve this. We're going to move the radical 3 over. That'll become negative radical 3. Divide by 2. Move the sign to the other side. It's now the inverse sign. Okay, and now we're going to go to the chart. So we want the angles where that have a sine value of negative radical 3 over 2. So again, I've got my charts handy. Okay, so sine radical 3 over 2, and we want the two angles that are in quadrants 3 and 4 because that's where sine's negative. So the 4 pi over 3 and the 5 pi over 3. All right, so yesterday, or the other day, we would have wrote 4 pi over 3 plus 2 pi k, or theta could equal 5 pi over 3 plus 2 pi k. So we've got two solutions, and then if I take 2 pi, so what we did the other day was we took 2 pi and we added it to this. Well, if you have a positive angle and you add 2 pi to that positive angle, you're going to get a number that's bigger than 2 pi. So for this problem, we only have two solutions. 4 pi over 3 and 5 pi over 3 are the two solutions that are within like one revolution. So that's it. That's your whole answer. Okay? Now, why did we even take the time to write this plus 2 pi k if adding that is going to give us something that's too big? Well, let me show you on the next example. Okay, so here's the next example. So we're going to move the sign over. So 2 theta equals the inverse sine of positive 1/2. So again, go to your chart. Sine is positive in quadrants 1 and 2. So write down the two angles that are in quadrants 1 and 2 that have a sine value of 1/2. And if you do that, you are going to get pi over 6 plus 2 pi k, or 2 theta could equal 5 pi over 6 plus 2 pi k. But on this one, we're not done yet. We have to divide by 2 to get the theta by itself. So we're going to divide everything by 2. So this is now a theta. Pi over 6 is now a pi over 12. But the 2 pi is now just a pi. So since this is just pi, if I add that to that, it is going to give me another angle that's still less than 2 pi. It's within one circle, and so I do need to include it. Okay, so let's keep going. We'll do it on this side as well. Or theta could equal 5 pi over 12 plus pi k. So I've got two answers. I got pi over 12 and 5 pi over 12. But also, if I add 12 twelfths to either one of these, so pi over 12 and 5 pi over 12, those are my first two answers. But pi over 12 plus 12 twelfths is 13 twelfths, which is still within one circle. In fact, that's just barely past pi. And if I add 12 twelfths to 5 twelfths, I get 17 twelfths, which again is less than 2. So think of 2 as 24 twelfths. As long as I'm less than 24 twelfths, I need that answer. I need to include it. Now, if you add 12/12 to either of these, you will then go over. So 13/12 plus 12/12 is 25/12, which is bigger than 2, so I don't need that. So these are the 4 angles within one complete revolution that would solve this equation. Okay, so you need all 4 of them. All right, so take a look at number 3. Number 3, I've got tangent. So remember, tangent has a period of 1 pi. So that's something sometimes we make a mistake on. I need to move the tangent to the other side. So tangent of 1. So the inverse tangent of 1. So those are the 2 angles that are in quadrants 1 and 3 that have a tangent value of positive 1, which would be pi over 4 and 3 pi over 4. So theta over 2. So this is what we did yesterday. We did one that looked very similar to this. So theta over 2 equals, what I say, pi over 4 plus pi k, so just pi. Or theta over 2 could equal 3 pi over 4. Oh, that's not right. 5 pi over 4. 5 pi over 4. I can hear you yelling at me through the screen. All right, 5 pi over 4 plus pi k. But we're not done. We now have to multiply everything by 2. All right, so everything gets multiplied by 2. So this is now theta. Multiplying pi over 4 by 2 would give me pi over 2, because the 2 and the 4 would reduce. So I get pi over 2. But I also have to multiply the pi by 2 pi by 2, which is going to give me 2 pi. Okay, so let's see what that does here in a second. Over here, 5 fourths times 2. Well, if you just multiply by 2, you get 10 fourths, but that would reduce to 5 halves. And then plus 2 pi k. All right, so let's see what we got. We've got pi over 2. That's good. And then we have plus 2 pi k. Well, again, if I add 2 pi to a positive angle, I'm going to get an answer that's bigger than 2 pi. So I don't need to add anything to that to generate any more answers. Okay? How about this one? 5 pi over 2. 5 pi over 2 is also too big. Okay? Think of a denominator of 2. 2 pi, one complete circle, would be 4 over 2. Okay? One complete circle, if this is pi and this is 2 pi, okay, that'd be the same as 4 halves. This is 5 halves. So this is a complete circle and then another quarter. We don't need that. Okay, it's actually the same angle as this, just these are coterminal angles. So we only need the solutions within one circle. This one only has one solution. There's only one solution within one complete circle. Now there's infinite solutions, but only one within one circle. Okay? All right. Take a look at 4. All right, now this one has a square. Okay, so let's see what's going to happen when we handle that. So I'm going to move the minus 1 to the other side. It's going to become plus 1. This is using an x as a variable. No biggie. Going to divide by 3, 1/3. All right, so now I can't move the tangent over. I don't have a tangent. I have a tangent squared. So I need to take the square root of both sides. Now, when you take the square root of both sides, you are going to get the positive and negative, just like from algebra. Okay, if you take the square root, we want all solutions, so you got to put the plus minus there. Now, we're also taking the square root of 1/3, which is the same as plus or minus 1 over radical 3, right? 1's a perfect square, so I can take the square root of it. But that is radical 3 over 3. Okay, so that's what we're going to see on our chart. Now, notice that plus minus symbol. We want the angles. Well, I guess I'm not done yet. Let me move the tangent to the other side. Plus minus radical 3 over 3. All right, so we want the angles that have tangent values of positive radical 3 over 3 and negative radical 3 over 3. Okay, so I want all 4 of these angles. I want pi over 6 and 7 pi over 6, because that's where tangent's positive. But I also want these two, because that's where tangent's negative. So I want everything. So x is going to equal, now, this is it. We're done. X equals, it's going to be pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. And then that's kind of our boundary. 12/6 is 2. So if you go anything past that, you're done. So this has all the solutions that you're going to need. All right, look at 5. Tangent of 2 theta. Okay, so we're going to move the tangent over. Tangent, inverse tangent, negative radical 3. So 2 theta could equal, so I need the 2 angles that have a tangent value of negative radical 3. So again, tangent is negative in quadrants 2 and 4. So it's going to be the 2 pi over 3 and the 5 pi over 3. So it's 2 pi over 3 plus pi k. Remember, this is a tangent, so it has a period of 1. Or 2 theta could equal 5 pi over 3 plus pi k. But still have to divide everything by 2. All right, so let's see what happens. Dividing by 2 just doubles your denominator, right? So now in this case, the 2 and that 2 could cancel. So you could get just pi over 3 plus, but then this is also getting divided by 2. So that's going to be pi over 2k. Let's see what happens over here. I got theta. Dividing this by 2, it's not going to reduce with the 5. So this is going to be 5 pi over 6 plus, and then pi over 2k. All right, so I've got 2 solutions, pi over 3 and 5 pi over 6. But I also need to see if adding these pi over 2's are going to give me more. I need every single solution within one circle. All right, so I am going to need some common denominators. I've got a 3, I got a 2, I got a 6, and I got a 2. How about we just rewrite everything as a 6 and see what that does? So this is going to be back to 2 pi over 6. This is going to be 3/6. Okay, if I multiply this by 3 to get 6, I need to multiply that by 3. So 3 pi over 6. And then over here, I've got 5 pi over 6 plus 3 pi over 6. All right, so let's see what happens. So we've got our first angle, 2/6. Now I'm not going to write that. I'm going to write pi over 3. And then I need to add 3/6 to 2/6. Well, that's going to give me 5/6. Okay. 5/6 is less than 2. So remember, so think of what our kind of cutoff is. Okay, if we want one complete circle, so we want all the way to 2 pi, 12/6 is our limit. We don't want to go past 12/6. All right, so now 5/6 and 3/6 would give us 8/6. So that's still under our limit. Now, again, I'm not going to write 8/6. That reduces. 8 and 6 both have a 2 in them. So that's going to be 4/3. And if I take 8/6 and add 3/6, I get 11/6. Okay, that's still under the cutoff. But if I add 3/6 again, that's going to be 14, and now that's too big. All right, so this one was a little different. But those are the 4 solutions to that equation. So you got to find all of them within one circle. Okay? All right, why don't you try to do number 6 and try to find all the solutions. So press pause and then press play when you're done. Okay? All right, so step by step, I moved the -1 over. It became 1. I took the square root of both sides. That gave me plus or minus 1, because 1 is a perfect square. I moved the sign over. So I needed the angles that have a sign value of both positive and negative 1, which would be pi over 2 and 3 pi over 2. But if you add 2 pi to either one of those, you're going to get an answer bigger than 2 pi. So there's 2 solutions on that one, pi over 2 and 3 pi over 2. All right, last couple examples are a little different. Now, it says solving a trigonometric equation in quadratic form. Now, actually, a couple of the ones from the first section were in quadratic form. If you look at number 4, if you look at number 6, I mean, that's a tangent squared, that's a sine squared. That's a quadratic, okay? But because there was just a sine or just a tangent, we could isolate the tangent, we could take the square root of both sides, and we could solve it that way. Well, number 7 is not going to be that way. If you take a look, it's got 2 sine squared of theta minus, and then it has 3 sine theta, and then plus 1. So when it says quadratic form, what they're saying is this should remind you of, and I'm going to use a different piece of paper here, something like this. 2x squared minus 3x plus 1. Okay, it's quadratic. It's got a squared term. It has what we call a linear term, and then it's got a constant. So that's what they mean by quadratic form. And this solves exactly like this. In fact, if there's too much going on here, okay, you've got quadratics, you've got squares, you've got things that aren't squared, you've got numbers, you got these trig functions, you can always take one of these and you can rewrite it in terms of x, and then you can solve this. Okay, so this factors. Okay, it's going to factor into 2 sets of parentheses. 2x squared, one of these has to be a 2x and one of them has to be just an x. That'll give you your 2x squared. The only way to factor a 1 is a 1 and a 1, or a negative 1 and a negative 1. And since we want our middle term to add up to negative 3, negative 1 and negative 1 makes sense for that. Okay, and again, check the OI. Okay, check your, when you FOIL, the outer would be negative 2x, the inner is negative 1x, and that would add up to negative 3x. So that's how that factors. So that means this factors into 2 sine theta minus 1, and then sine of theta minus 1 equals 0. Okay, same thing. It's just, it factors into 2 sets of parentheses. You've got 2 things. The reason we factor is to create a multiplication problem, because we have 2 things that are multiplying together to equal 0. So either this equals 0, 2 sine theta minus 1 equals 0, or this one can equal 0. And this is just sine theta minus 1 equals 0. So now we have 2 equations that are just like the ones that we did on the top. Now we just have 2 small little equations, like this one right here. I'm going to move the 1 to the other side. If you'll allow me, I'm going to move the 1 to the other side. That'll be 1. It's then going to get divided by 2, so that's 1/2. And then I'm also going to move the sign over there. So theta equals the inverse sine of positive 1/2. Okay, and then we're going to go to our chart. We're going to write down the 2 angles, one in quadrant 1, one in quadrant 2, that have sine values of 1/2. So that's going to be pi over 6 and 5 pi over 6. Pi over 6 and 5 pi over 6. Now, again, if we add 2 pi to either one of these, again, we only want solutions that are between 0 and 2 pi. And because both of these are positive, you add 2 pi to them, you're going to get an answer that's too big. Okay? And really, the only time that comes into play is, like, look at number 5. Why did 5 have extra angles? It's because the last thing you did, there's a 2 out in front of the theta. And so, and this one was a tangent. So this one can create other ones. How about number 2? Okay? There's a 2 in front of the theta. So that 2 pi got divided and became a 1 pi. So the only time you really have to worry about these extra angles that could be created is if there's like a number in front of your theta. If there's a 2 in front of it, a 3 in front of it, a 4, something that you're going to divide that 2 pi by to make the 2 pi a lot smaller. So it actually could be something that could add to create more angles. Okay? But for this one, those are the only 2 that are going to come from this side of the equation. But this one also is going to generate an answer. So sine of theta equals positive 1. So theta is the inverse sine of positive 1. So again, go to your chart. There's only one angle that has a sine value of 1, and that's pi over 2. Okay, 3 pi over 2 is negative 1, so just pi over 2. So we've got 2 answers here. We've got 1 answer here. So there are 3 answers to this problem altogether. Okay? All right, last one. Now, the last one is going to turn into something that looks like what we just did. But it's going to start out wrong. There's something wrong with this problem. Okay? And it's the fact that we don't necessarily have like terms. I know it looks like we do. We have a cosine and we have a cosine. But this is a cosine of theta, and this is a cosine of 2 theta. And they're not the same. If all we had was a 2 theta, okay, we can solve for that. We can move everything to one side, and then the very last thing we do at the end is we're going to divide everything by 2. But this is a 1 theta. They're not the same. But if you recall back to when we did the double angle formulas, so I'm going to grab my, okay, so here's my notes with the double angle formulas. There were 3 double angle cosine formulas. There was this one, which is the one that we use when we do double angles. And then there was these other 2 that I had on the notes, and I told you, you know what, we're not going to use these when we use the double angle formulas. But here's a place where we can use them. I can replace the cosine of 2 theta with one of these expressions over here, and then I will just have a regular theta, and I won't have a 2 theta anymore. So in other words, I will have like terms. Now, this term is being squared, and the other term that was in the problem was not squared, but that's okay. That's just a quadratic like over here. The fact of the matter is, if I can get both of these to say cosine of theta, then I'm good. Okay? So, take a look at those formulas. This one says 2 cosine squared theta minus 1. If I replace the term cosine of 2 theta with that expression, so the cosine of 2 theta, I'm going to replace with a 2 cosine squared theta minus 1. Okay? That whole thing is going to get replaced with that expression. Now, I still have a plus 3. And then I have a 5 cosine theta. 5 cosine theta. But now everything's in the same terms. Now, I put parentheses around to kind of show that this is one entire thing that I've got in the equation. I don't really need the parentheses because the only thing that's outside the parentheses is a plus 3. So if there was multiplication where you had to distribute, then it would be good to have those parentheses. But if you just have addition, we don't need them. So I can drop the parentheses and I can actually combine these. 2 cosine squared theta minus 1, minus 1 plus 3 is going to be plus 2. And then when you have a quadratic, you want to get everything to one side. Okay, so I've got a 2 cosine, and you also always want your squared term to be positive. When you're going to factor, you want that to be positive. So we want to leave this one where it's at. We want to move the 5 cosine over here. So 2 cosine squared theta minus 5 cosine theta plus 2 equals 0. All right, so now this is going to factor. I'm just going to set 2 sets of parentheses, and I'm going to treat the word cosine like it's a variable. I know that this, for the first to multiply together to give me 2 cosine squared, I need one to be a 2 cosine, and then I need the other one to just be a cosine. That'll give me the 2, and then the cosine times cosine will give me the cosine squared. So that's how the beginning part of my parentheses are going to factor. Now, the last, that's going to be factors of 2. Now, factors of 2 could be 2 and 1, or it could be 1 and 2. Also, both of those could be negative. So let's think about what we're doing. We're trying to multiply in a way that our outer and our inner add up to negative 5. Okay, if I put negative 5. So I'd really like to have like a negative 4 and a negative 1. When these multiply together, if I could get a negative 4 and a negative 1, I'll get my negative 5. Well, if I put a negative 2 here, so that 2 and that 2 are going to multiply and give me negative 4. That means this is a minus 1. And now when you FOIL this, you will get a negative 5 in the middle when you do your outer and your inner. So that's how it factors. Okay, so now this is going to split into two equations. 2 cosine theta minus 1 equals 0, or cosine of theta minus 2 could equal 0. All right, so now we're just going to solve each of these separately. Again, I'm going to move the minus 1 over. I'm going to divide by 2. I'm going to move the cosine. You could do all the steps if you want. Okay, so now I'm going to go to my chart. I'm going to figure out where cosine equals positive 1/2. And looking at your chart, it's going to be pi over 3 and also 5 pi over 3. The angle in quadrant 4, that's where cosine's negative. Then I'm going to come over here and I'm going to solve this. I'm going to move the 2 over, I'm going to move the cosine over. Theta equals the inverse cosine of 2. Alright, now we got a bit of a problem. If you look at your chart, I do not see a 2 there. In fact, you're not ever going to see a 2 there. Let's think back to our cosine graphs. Cosine starts at 1, goes down to negative 1, back up to 1. There is no angle that has a cosine value of 2. So this doesn't give us a solution. It can happen, okay? So this doesn't give us any answers. This gives us 2 answers, so those are our 2 solutions. So for this one, I used a little substitution trick to get my variables the same. This over here, I could have had the word sine over here. Now, if I had the word sine, it probably would have been a little bit more obvious that these were not like terms. But if that was a sine, I could have done the same trick. I could have replaced the cosine of 2 theta with this formula, the one that has the sine in it. Okay, and then my equation would have nothing but sines, and I could solve it just like I solved the other ones. Okay, so keep a lookout for that. Again, the trick is if you have 2 and one is a double angle and one is not a double angle, that's how you know you need to use some substitution. Use a little trick there. If all you have is a double angle and there isn't another one to be not like terms, then you can just solve it normally. Okay, so take a look at the problems on your worksheet and let me know if you have any questions. Thanks, guys.